Hey everyone, if you've ever been excited to run a new language model on your own machine, only to get slapped with that CUDA out of memory error, well, this one's for you. We're going to cut right through all the noise and finally make sense of the math behind your GPU's VRAM. So let's start with a question I know is on a lot of your minds. You've got a 16 gig GPU, you've got a 13 billion parameter model, and you think, yeah, that should fit, right? I mean, the math seems to work out. So why? Why did it crash? It is honestly one of the most common and, let's be real, frustrating roadblocks when you're building local AI. And here's the good news. You're not bad at math, not at all. The problem is that this simple comparison of model size to VRAM size, it's just incomplete. You're missing a few really crucial pieces of the puzzle. But don't worry, there's a much better and frankly, simpler way to think about all this. So here's our game plan. We're going to start with what I call the VRAM guessing game and show you how to stop playing it. We'll cover the one and only formula you really need, figure out what actually fits on your hardware, and then uncover this thing called the hidden VRAM tax. After that, we'll dive into some common traps and finally get you from just guessing to actually designing your AI systems with confidence. All right, first up, the VRAM guessing game. We've all been there. The goal here is pretty simple. Let's move away from those frustrating, unpredictable crashes and start building systems that just work, predictably. So how do we stop guessing? Well, it all boils down to what I like to call the only formula you need. Seriously, this is pretty much the single source of truth that's going to let you figure out your VRAM needs every single time. And here it is. This is the whole enchilada. The VRAM you need in gigabytes is roughly the model's parameters in billions times the bits per weight, all divided by 8, because there are 8 bits in a byte. That's it. This one little formula explains pretty much everything, from a full-fat FP16 model all the way down to a super quantized 4-bit model. Now, here's where it gets really practical. That formula breaks down into some super easy rules of thumb. For a standard FP16 model, you're using 16 bits per weight, so you need about 2 gigs of VRAM for every billion parameters. For 8-bit, it's a clean 1-to-1 ratio. 1 gig per billion params. And for a typical 4-bit quantization, you need half a gig per billion. Seriously, if you remember nothing else, just burn this into your brain. 2x, 1x, and 0.5x. Okay, theory is awesome, but let's get real. Let's talk about hardware. This brings us right to our next section, what actually fits your GPU. This is where the rubber meets the road, and we apply that formula to the gear you're actually working with. And this table just lays it all out, doesn't it? It shows the real-world trade-offs you have to make. Let's go back to that 16 gig GPU from our original question. See, at full FP16 precision, you can maybe squeeze in a 7 billion parameter model. But if you quantize that sucker down to 4-bit, boom, all of a sudden you're running a 25 billion parameter model. So think of this table as your practical cheat sheet. It's all about that constant balancing act between model size, performance, and quality.
But hang on a second. If a 13 billion parameter model at 8-bit is about 13 gigs, why did it crash a 16 gig card, right? This is the key, and it brings us to our next big idea, the hidden VRAM tax. Because loading the model weights, that's just the down payment on your total memory bill.
So yeah, your model is still crashing because the math we've done so far only covers loading the model's weights into memory. That is literally just part one of the story. The rest of your precious VRAM is being quietly eaten up by a bunch of other critical things that you don't even see until, poof, you're out of memory. So who are the culprits? Well, here they are. The KV cache is a huge one. It's what helps the model generate text quickly, but its size grows and grows with your context length. It can easily eat up gigabytes of VRAM. Then you've got activations, which are like the model's short-term memory. You've got batching, framework overhead. They all add their own little tax on top of the model weights. So as a system designer, what do? Well, here's a good rule of thumb. Figure out the memory you need for the weights, and then add a safety buffer, at least 10 to 30%. And listen, if you know you're going to be pushing super long context windows or running a lot of things at once, you're going to want to budget even more than that. Okay, let's get into some of the weeds here. Let's look at a few common traps and nuances that can really throw a wrench in your calculations. We're going to demystify 2 big ones, mixture of experts models and the GGUF file format. The mixture of experts trap. This one gets a lot of people. You see a model described as 8x7b, and you might think it runs like a 7 billion parameter model. Here's the critical difference. The total number of parameters, all of them, determines your memory footprint. You have to load all the experts into VRAM. The active parameters, that smaller number, that just determines the compute cost, how fast it runs.
So for MOE, remember, memory cost does not equal compute cost.
Next up, GGUF. Look, it is an absolutely incredible format that has let so many of us run huge models locally. It's a game changer, but it often gets talked about like it's some kind of magic VRAM cheat code. And it's not magic. It's just very, very clever engineering that was built for a specific job. And this is the part you really need to get. GGUF is a special container that's been hyper-optimized for runtimes like llama.cpp, especially on machines that are designed to use both system RAM and VRAM. So when you see those amazing memory numbers, they're only true in that specific context. The second you try to load that same GGUF model into a different framework, guess what? The weights might get dequantized back to a higher precision, and your VRAM usage can just explode. All right, we've covered the core formula, the hidden tax, and the common traps. So let's bring it all home. Let's talk about moving from guessing to designing. This is all about giving you a simple, powerful mental model so you can build your own systems without the headache. It really just comes down to these 3 steps. 1, you always start with that core formula to get your baseline memory for the model weights. 2, you add a safety buffer for that hidden tax, the KV cache, the activations, all that other stuff. And 3, you adjust that buffer based on what you're actually doing. Are you running long context, high concurrency? This is how you design a system that's robust and that actually works. And this right here, this is the big mindset shift. Once you internalize this process, you stop being a passive user who's just asking, hey, can I run this model? You become an active system designer who starts asking a much more powerful question. Okay, how do I want to run this? Do I need the highest quality, so I'll use less quantization? Or maybe I need to shard this massive model across a few GPUs to handle its full precision? The power shifts back to you. And that's when building with local AI starts to get really, really fun.